Why did you close the door?
I don't know what the door.
You sick?
That might be. I definitely have something in my throat. My friend's kids were yeah. And so I don't want, if I am sick, I don't want y'all to get sick because the pictures he sent me were disgusting.
Oh, no.
I'm not going to go into detail. Ready to learn?
How are you doing?
Oh, not so good. Hence the mask. Hence the feelings. It was very difficult to try and prepare today because we're going to be jumping between basically 3 books.
We say that on like every lecture.
I mean, it's weird to prepare a class that you've never done before in a style that is like not natural. The probability section was easy, right? You basically just do math.
Yeah.
You just gamble, right? You just make up fun bets. This one is a little less straightforward. Okay, so we were talking about inner and outer products. That's not belly button things, right? What's the inner product again? You remember?
The inner product.
Notice I have not remodeled the issue.
Wow.
Wait, the inner product is the cross product, and then I think the outer product is the dot product. The other words, inner product is dot, outer product is cross.
Yeah. And why do we call them something new? Why not just use cross product and dot product?
Because we're using the sum formula or sum notation.
It's like more in general.
Yeah, it's more general, right? Because when you're thinking about
There is. And there's no product.
yeah. Right? Okay, so when we take the cross product between 2 vectors, we get a vector. Yes. And when we take the dot product between 2 vectors, we get good. So let's reword those. When we take the dot product between 2 first-order tensors, what do we get?
You get a 0.
0 coordinates, right? So it reduces the order of the tensor. So an inner product does what? Reduces.
Reduce the word.
Good. And a cross product does what? Or an outer product does what?
Nothing to the order.
Right? So in fact, we could use a cross product between 2 tensors, and we did quite often. So in fact, we talked about this in the context of something like this. T I J could be written as U I V J. Right? So you can actually go up. You can create a tensor from 2 vectors. Second order tensor from 2 first order. Another thing we can do is we can have the gradient of a tensor or of a vector. So you could say, for example, T I J could be dvi dj. Right? And then in coordinate language, you would write something like this would be the same as. Right? And that would form the components. Like, sorry, the tensor. Make sense? Okay, these are just tensor operations. Okay, so let me introduce you to another fun tensor. And this one is really going to practice these ideas of understanding our indices. And then we're going to talk about We're gonna go back to these ideas of dot products and cross products. We're gonna talk about something called the metric of flat space. Okay, so you're familiar with this one already? Correct? What's that? Good, what is it?
So it's one when I is equal to j, and then zero everywhere else.
Okay. So let me introduce you to this one. Have you seen this one before? Okay,
So it's the same thing from I is equal to j.
what's it? This is the Levi-Sativa tensor. And what rank is it? Third, right? So this one's really interesting, okay? And it works like this. It's +1 if I, J, and K are an even permutation. It's -1 if odd, and it's 0 otherwise.
Then odd and perfect.
Good question. Good question. Okay. So the best way that we can do this is to write it out. Okay. So what is a permutation?
Away or something, I don't know.
Remember when we were talking about the ways of counting for probability? And we said, for example, you know, if I put these 3 books on the table here, like this, and I think about all the ways that books can be arranged, I can have A, B, C, or I can have A, C, B. This reordering is a permutation.
Yeah.
So this would be an odd permutation. Because this is A, C, B. That's one change. And this would be an even permutation.
So
Because
it's
it's
odd,
E, A, or sorry, C, A, B.
it's odd, but not in numerical order.
Well, for every change that we make for I, J, K, right? That will be a permutation. And you're going to keep stacking them until you get something that's back to what it was. The easiest way to show this is to do it, I think. Okay. So I'm going to give you a matrix. And then I'm going to show you how we apply the Levi-Civita tensor by showing you this really fascinating use of it. Okay. You remember what the determinant is? The determinant of a matrix.
Yeah, or for like a two-way matrix.
Yeah, but what does it mean?
There.
Reasonable.
What is the determinant of a matrix, folks? That really checked out week 9, huh? How much St. Patty's I say? Not enough vector count?
Okay, I got it.
No, you got it.
Wait, I found the page. Like, you want like the purpose of it?
No, what does it mean?
Yeah, what does it mean? Like,
Um, looks similar to like the cross product.
Sure, it looks similar to the cross product, right? It's a way of seeing.
I'll tell you why you do
Okay.
it.
If you wanted to take the inverse, you would need the determinant, right? You need to be able to divide by it. The determinant is basically telling you how big the matrix is, what the size of it is. Something similar to that, right? In this case, when we're calculating the determinant, we could use the Levi-Civita tensor. And this is going to be the easiest way for us to learn how to use these permutations. Okay? We're going to come back because we're going to pick a big old asterisk here. Because you don't know what a determinant is. We're going to come back to that thought afterwards. But for this purpose, let's evaluate this in real life. So first, let's take A. So what is it? A is going to be a tensor that looks like this. Okay. Now I told you this. I said I made this claim that we can find the determinant simply by looking at all of these individual components and using here Levi-Civita tensor. And of course, we have a dual index here, here, and here. So we'll be summing over those, right? Okay. So how do we go about getting the individual components?
You're just making like some matrices.
What's that?
No, I thought originally like with like ALI, that was like a submatrix,
What do you mean a submatrix?
like just like a, like taking like with ALI would be taking like the L row and the I column, and making that a submatrix.
Are you saying submatrix?
So
What's a submatrix?
well, submatrix is just like another block, literally just a matrix inside of a matrix. They use like make a smaller one. So it's like if you have like a 4x4, you just make it 2 by 2 out of it. Like you use it.
Okay. Okay. I hear what you're saying, but that's not necessary.
Yeah.
So here you have Li. What does this mean? ALI.
L row I column.
Good.
So like in that position.
Good.
Okay.
That's it. That's all this means, right? What does this mean?
M row.
Good. What does this mean? Good. What does this mean? Who the fuck knows, right? Okay, so let's do it. Okay, let's pick the first one. Okay, so here on the left-hand side, we know that L, M, and N, right? These indices need to come out later, such that we can have this determinant. Right, if we want to calculate this on its own. So let me ask you the first one. Okay, if I, J, and K are all the same, 1, 1, 1, what is this?
Oh, it doesn't be multiplying everything by it's just like
I don't understand even in odd permutations still. So then
See if we can write this out. I think that's like the easiest way to do this, but I'm wondering. Okay. If you have right, 1, 2, 3, right, versus 2, 1, 3. How many permutations went into 2, 1, 3 versus 1?
probably one. They could have done like 20 times.
Right, they're gonna start canceling out. Right, because as you do them over and over and over, right, you could do, you know, 6 or 7 permutations and get back to where you are, but then that's not different from where you started, and therefore it's a 0 permutation.
Only one number has moved, so it's one permutation.
Yeah, well, 2 numbers have switched places, which is a 1 move, right? So if I and J switch places, That's one permutation, and thus is an
Uh,
odd permutation. If I and j switch places, and then k and I switch places, that's an exactly, right? So there's not that many choices. Does that make sense?
Yeah.
Okay. So let's imagine for a moment how we can do this. Okay. So we're going to end up with this at the end on both sides. So all we have to really think about is if we want to calculate this here, we just need to know all of these components and the signs. Okay. So what's the first one we could use?
And go where they're both high.
Here and there.
So what is our frame of reference for like different number of permutations? That's why I'm confused about in this particular example. Because with the, I forgot the name of the new delta that we just wrote in the board. But with that, you need like you need to know either like even or odd amount of permutations. But how can you say that something's changed if you don't have a frame of reference for where it initially was? Like, well, it's like, what is the thing that we should be comparing? Yeah, for like what is the original so we can count the number of changes?
It's right here.
There was something it would be like A L 0 something.
What do you mean 0?
And we have to sum the A times the epsilon.
Yeah, well, I mean, it's a multiplication of these three components, right? So does 0, 0, 0 exist? No, because it's not part of the tensor, right?
Oh,
Starts at 1, 1, 1. Right? Does 1, 1, 1 exist? In the Levi-Civita tensor?
No, because
No.
it's zero.
Because it's 0 otherwise. Okay, let me write this another way. Maybe this will be more helpful. Okay, there's the relationship between the Levi-Civita tensor and our famous friend, the Kronecker delta.
I guess my question is because it's 2D, do we sum it like 1 and 2? Or do we add it together 3 times?
2.
Because A is 2D, but for the I, would you plug in 1 and 2?
1 and 2.
You have to sum over a number of things. We're summing over 2. Is it second rate?
Well, remember that the order here doesn't tell you how many to sum over, right? Because L is the length of the array.
So what number do I sum over?
So how big is the array?
3 by 3?
So what would you sum over?
3?
3. You have to sum over 3, right? Because otherwise it's not a full sum. Right or wrong?
I was not confused.
If you had, yeah, no, it's okay. If you had a 10 by 2, right? Then this would be 10 and this would be 2. No?
Yeah.
Okay. Okay, this is very confusing. That's okay, that's probably my fault. As I mentioned at the beginning. 1 slightly sick. And so maybe it's not coming across well.
Wait, so for this one, is it an odd number of permutations? Because but it's what is the name of the new delta again?
Levi-Civita tensor.
Levi-Civita tensor. So with the Levi-Civita tensor, on the left-hand side, which is LMN equal to Levi-Civita of IJK, isn't that like 3 different permutations because you change like all the variables? Or am I just like reading that?
Okay, so let's remember one thing about what's dummy and what's free.
Yeah.
Okay, so if they're repeated, they're summed over. and therefore they're dumb. If they're on this side, they have to match on this side, so they're free. Right? Okay, let's have a look over here and see if this will help us understand it, and then we can go back to doing the determinant. Or we can just throw this away and we can try again. Okay, so if this doesn't help, we're just gonna go directly into special relativity. Okay, here's the product of two Levi-Civicek tensors. Ugh, gross, I don't understand it. Now you want me to multiply them by each other? Okay, but what does it say? It says IJK, KLM. So how many free tensors do we have and how many dummy tensors do we have? Excuse me?
Three free and then free dummy.
One is dummy. Which one is it? K is the only dummy. And there's 4 free. So let's look on the right-hand side. What do we have? What's that? Oh shit, I wrote it wrong. That's why. What do we have on the right hand? They're all dummy variables, right? Okay. No, so they're all free variables, right?
Okay, multiply by each other and then sum over them.
Well, so for example, these ones here, right, are going to act to do what? Delta ij says that I equals j, and it becomes 1, otherwise it's 0, right? So this one here acts to do what? Yeah, either I becomes L or L becomes I, right? And similarly, either J becomes M or M becomes J. I becomes M or M becomes I, and J becomes L or L becomes J.
I wonder what happens to it becomes 0. So 0 is 0 or 1 is 1.
Is it? Here's the interesting part: is it's not only 0 or 0. Otherwise, that would be useless.
If I equals J,
It's 1, -1, or 0.
Yeah, you can have 1 minus 0.
Yeah.
I can see why it's okay. Yeah, I can see why they're mathematically.
Does that make sense?
this one, how do you not make the epsilon be 1, 1, 1 when you're adding it?
How do you make the epsilon not 1?
Because you're summing over I, J, and K. So it's gonna be, when you do the first number in the sum, it's gonna be 1, 1, 1 on the epsilon. The second one, 2, 2, 2.
Okay, so what is 1, 1, 1?
Anytime that K.
I don't know. You tell me what happens at 1, 1, 1. It's not that it can't happen, it's that it becomes
You said,
0.
I thought you told them you can't do that.
What do you mean? When you're doing the sum, you're allowed to do all of the indices, right? I'm just saying you can't repeat I. Because, you know, for our notation, the dummy variables need to be able to add up, right? But of course, you have to sum through all the correct numbers.
Then the whole thing's gonna be 0. Next one will be 2, 2, 2, then 3, 3, 3.
Is that all there is?
You said there's 1, 2, 3.
Also 3, 2, 1. So 1, 3, 3, 1, 2.
Remember that it's a triple sum here, right? The I is with the I, the J is with the J, the K is with the K. Right? It's all of the indices. It's 1, 2, 3, 1, 2, 3, 1, 2, 3. I just can't draw it on the board. Why can't I draw it on the board? What? Okay, what is the rank of this tensor? Second order. Can I draw this tensor? It's third order, because I don't have board coming out of the board. Right? You see that or not? So. Okay, I would need
No, I
this.
just said that. I'm still not in something.
Maybe this wasn't a good application of this one.
Well, I just don't know how to add 1, 2, 3. Like,
I don't know.
oh.
Sorry, say that again?
In my notes, when you're adding together the all the different indices. You just made all of them 1 and all of them 2 and all of them 3. But I think I have my notes down wrong of how to add them together for the repeated indices.
Right, okay, so
So I don't know how to add it together when it's not just everything's 1 in the.
yeah, so okay, so the problem there, I think, is that before, it's not simply that they're, 1, 2, 3 only, that would be the diagonal components. It's that you have to sum every single component, right? So if, for example, I was walking through this, it would be 1, 1, 1, 2, 1, 3, right? 2, 1, 2, 2, 2, 3. So similarly, you walk through all the components here. 1, 1, 1, 1, 2, 1, 1, 2, 3.
Okay.
And now the 1, 2, 3 has what? Yeah, I mean, let's write a few of them out, right? Okay, so here's the first one.
Oh, the mega one.
Yeah. Is it still 3?
Yes.
You can't say actually it's 3 or 1.
No, that's not a permutation, right? Permutation means that you switch the order.
The only things I'm gonna say are with 3, 2, and 1 are all there.
Exactly. Okay.
So then 1, 2, 3 is not a permutation?
So it's also 0. Or because 0 is not even or odd.
0 is even or odd. In fact, 0 is the most something type of number. Is it even or odd?
Even.
It's even. It's dramatically even, right?
That makes sense.
Why is it dramatically even?
There's nothing left over.
You divide by 2.
Yes, 0 divided by 2 is certainly 0, right? Okay, well, I didn't make up the math. Okay, so what's this?
1.
Yeah. Maybe this is how I should have started. I'm sorry, folks.
Okay.
So this was 1, 1, 1. Let's do 2, 1, 1. Good. Okay, let's do this one.
3, 1.
Oh
No,
negative
-1.
1.
Now
There we go. Yeah, this is where I should have started. I'm sorry, folks. I don't know why I did all this other stuff. Just fuck with your head. But this is straightforward, no?
Yeah, I just didn't understand what.
Okay, so then just forget all the rest of this. We'll try and do it maybe in a homework problem instead.
No.
No, fuck that. Okay, well, what about this one?
Oh, that's odd.
Plus
Negative 1.
I thought that was a decent permutation.
What?
It is.
That's odd.
No, it's both right. An odd number of permutations and switch.
Show me. How's that?
1 and 3.
You switch 3 and 1, so you switch those positions, that's just a single permutation. From 1 to 3.
That make sense?
Yeah.
Yeah.
Yes.
So single permutation is.
Negative 1.
That was negative 1.
What? What's that one?
And that should, yeah, that should be positive 1. Permutation switches 1 and 3, and then 3 and 2.
Okay. Sorry, folks. That was maybe as brutal for me as it was for you. We don't get it. What do you say?
Let me speak of 2 to 0.
Did you do?
Yeah. Actually, and then taking the 3.
Okay. Let's do this one now for a second here. I know that this looks useless, but I promise that it's not. And in fact, you may encounter it at some point in your life. What values can this take?
10, negative 1, 1, 0.
What are the conditions for that?
I guess if I equals L and J equals M, then it's one.
If I equals L and
J equals M.
good and
I think that's all you need for it to be one.
J and I cannot be the same. Right? J can equal M, good.
Why can't J equal I?
Well, show me what happens when J equals I. If J equals M and it equals I, right? Then it's zero.
Oh, so that would be positive one. In this case, it'd be positive.
Oh, then everything would be the same?
Yes, and therefore would disappear, right?
Okay.
So what, so you said negative one or positive?
I said positive one.
You agree? Agree? Yeah. You just saying that because everyone else says it?
Wait,
Well, I'm writing them down, so.
Okay, so say it again.
I think
Walk us through
it should be positive one because if I equals L,
it.
and in the
I equals L, then this becomes
one,
good.
and
This
then the J
becomes
equals M, but not equals to I, then that becomes 1 times 1,
And that is zero.
and then that has to be 0, so it's 1 minus 0.
so I equals M or no?
It does not equal M.
Ah. Okay, so what's the other one?
So you have
I equals M.
So it's not equal I or something.
Well, you tell me, what is it? I don't know, some bullshit like that.
Yeah, I would.
Is it I?
what do you- trying to-
Yeah, because then if I equals M and I doesn't equal M, then J will also not equal that I, which equals M.
What?
Sorry. There's too many letters.
Okay, let's do the first one. I equals M. Okay, this one is,
One,
and J equals L.
one.
Good, and this one here?
If it does not equal I, it would be zero,
Good, and this one here?
zero.
Right? Yes or no? You're just saying it like that, so you're shrugging, but it's right. Okay, and then the last one?
Zero, L equal.
0 if, yeah, in a second. I is not equal L, I becomes.
Yep. I'm not feeling insecure. Okay, so you know, this is sort of the tricky part about moving up in tensor rank. You know, as uncomfortable as we felt with matrices, now we're dealing with something with 3 indices, and we're headed towards more, right? Okay. So I know we don't like reading the book. I know we don't like watching the lecture outside of class, and maybe this one at the beginning won't be very fun to watch either. It may be more confusing than anything else. But I do recommend really going back and looking at those basics, because you're gonna get super lost as we go from book to book to book.
So sorry.
Okay, all right. So the first thing that we want to do is we want to think about why the fuck we were doing this in the first place. And we've kind of like moved away from any of the physicality of what we're doing. And I want to kind of bring us back there to motivate the work for a moment. So we were talking about creating a form of mathematics that would be able to be rotated, for example, And then you would have properties of that rotation. So let's say you start with an oriented vectors like this, and you change your coordinate system. Our expectation should be that those vectors don't change, right? That would be weird if we changed our coordinate system and we saw something physically different in the world. Does that make sense? So we would say that there are certain vectors or quantities, physical quantities, that are invariant under transformation, right? We said that word before. Okay. And we also say that there is a specific type of tensor. Delete it all. Okay. All right. So let's make a property of a tensor such that this second order tensor T is going to be okay, so let me say this differently. You already know of an invariant tensor, that's the identity tensor, or also the Kronecker delta tensor, right? Those are both invariant under any rotation, because all they do is they reduce back to what they were originally. So you could say any tensor like this, and let's use a new coordinate system. We're going to call it T prime. It just indicates that we rotated it somewhere or the other. And it's going to have the same indices, right? Because it's required to. Okay. And we did that through two transformations. Remember, we used L for our transformation matrix. Okay. This. Okay. So what are we saying here? We're saying something along the lines of there are properties in certain matrices where under transformation, they're not changing. Right? And we would call those isotropic or invariant tensors. Some physical applications. We'll just jump ahead here. So when we think about, for example, angular momentum, it's not just what the ballerinas do, right? It's also like something that we have to measure. And in particular, you know, you have a ball on a string. You're like, okay, ball on a string, that's pretty easy to calculate. But for more complex things, it becomes quite tricky. Okay. So we would say something along the lines of, excuse me, J, which will be our tensor here. Well, we're going to write it here in vector notation. Sorry, vector notation. And you could reduce this here. You could say J, let's write it in, sorry, tensor notation again. You could write it like this. You may have seen this one before. I omega. Well, let's put the indices in here to demonstrate how powerful this is. This is really I, L. And it's a second order tensor. And that second order tensor has the properties I. I'm not gonna write all of them. But it's the integral y squared plus, we're gonna imagine that it's 3 and 5 coordinates. Right. Likewise down the diagonal. For the other ones, like this. Here, and then go off axis x. The row is the density distribution. You may be familiar with something similar to this, or maybe not. But these diagonal elements are what we call the moments of inertia. You've heard that before? Okay. And the off-diagonal elements are called the products of inertia. Okay. And you don't have to memorize that. But I just want to show you that they're ubiquitous in the way that we use them in physical mechanics. Similarly, if you don't really care that much about, like, for example, measuring the interior of planets, which is what this might be used for, you have a non-rigid object, so you measure the moments of inertia inside of the planet. You might be more interested, say, in the crystal structure of crystal structure of material. And you might say to yourself, well, okay, I have this material that I built, and you apply a voltage to it. And I'm going to see how electricity conducts through it. Well, you may remember, hopefully, everyone here remembers from this fine book, that you have these two wonderful relationships. You have M, the magnetization, is due to the susceptibility, and the H, right? Remember that? What was H again?
H is, isn't it just called H field? There's no like, field.
Yeah, it's just the H field, but what does it like feel like?
Like the it's like the atom.
It feels like magnetism, yeah.
It's modified next.
Exactly, like a modified, like a vibing magnetism.
Yeah, because it's like in a material.
Diagonal was the moments of inertia, what was the off
The
diagonal?
products. So these are the moments. And you can find this online. I'm not going to write them a lot. And these are the products. They're more over here too. So you remember that was cool, right? Okay, we always just assume that that was like a number, like 4 or 2 or something, right? But of course, that's not really how the world works. So maybe the magnetic susceptibility varies along different orientations in the crystal structure. And that would mean that this magnetic susceptibility or magnetism is dependent here, right? And so the magnetic susceptibility may be a similar. Similarly, you can think about the conductivity, which you want to measure the conduction of electricity through some element. So this is going to be annoying, so we're going to use J, of course. Shape. We apply an electric field. There's J again. But maybe the conductivity varies in the structure. And so almost everything you do in real life is not isotropic, right? I mean, maybe to first order, but first order was done in the 1900s. And so now we have to do several orders above that. So majority of the materials that we deal with, they have unique properties in every direction. Right? Not only do we have to measure moments of inertia for non-regular bodies, we have to consider, for example, the susceptibility to magnetism and to electricity in various crystal directions. Okay. 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 All right. That's this is going to take us to something called the metric tensor. And so I think in order to really discuss the metric tensor in a meaningful way, we need to completely stop thinking about tensors and talk about special relativity and general relativity. Because we've been talking about three vectors for a long time. And we introduced something called the four, right? And so it was as though our minds were already fucked enough by the fact that we have now three-dimensional tensors, or third-order tensors. We're going to, of course, be thinking of space itself as part of the fabric of a larger thing called space. Okay, so the motivation here is associated with the idea that physics needs to not change under translation, rotation, etc. Right? So the same reasons why we did tensors before, we say that the physics of the world should be invariant in a non-accelerating frame. That's the first tenet, right? That's this principle of relativity. Okay, so if we go back to this book here, our good, faithful companion, we go to the very, very back. It's this one. There's the special relativity, and this chapter in particular, we just have two rules. The first one is that the speed of light is a constant, right? We're not going to ask why. We're not going to ask how. We're going to posit that that's true. And everything that we do henceforth will follow it. Okay? All of the math that Einstein would undertake in the early 1900s were made possible by tensors, by Hilbert, who was a mathematician. He had to create Hilbert spaces before they could be used to describe general relativity. Okay, so we have these words like inertial. So what's an inertial reference frame? Not accelerate, which is just another way of saying. So we have to say the two famous postulates. One is the principle of relativity. Okay. Physics stays same in all inertial. Okay. And then G. Light. You ever wondered like what the world would be like if someone hadn't chosen C for speed of light? No. I mean, just like what? Why the letter C? Like C is a constant.
You don't really see from
I know, right? It's very convenient. But like, what if it was S
yeah,
for
like,
speed? You know, like E equals ms squared. Like that doesn't sound as cool. Okay. Sorry. So with these two principles, we have to be able to transform from one coordinate system into another. We already knew, for example, the motivation behind this was to address issues that could be seen in physics. But the way that we explain it to people maybe who are learning for the first time is the idea that if you're sitting on a train and the train is traveling, and you make these observations about the world, such as the speed at which clocks go, the rate at which time is moving, All of these things need to be consistent between the person moving on the train and the person standing on the station, right? And so you have to be able to transform between these two frames. So Galileo said that you could simply add speeds together, you would get the resultant speed. And Einstein said, correct, no. So Einstein's velocity rule is, of course, this. As a result, the velocity of A from C, the velocity of A from B, and the velocity of B from C, but moderated by 1 plus B A B times B east over C squared.
It's like one minute, how fast things can go with that, in the denominator.
Yeah. That's correct.
If it's small, it's not worry about.
Yeah, you can just ignore it, you can just 1 over, like, at worst, it'd be like 1/0,
Right, yeah, so we have to remember that we need to look at the limits, of course. So if these are small, then you get Galileo's addition rule back. And if these are large, let's say V AB, for example, was C, what would you end up with?
is equal to C, yeah. It is 1 plus 1 over C.
Yeah.
Denominator.
Yeah.
Yeah.
It's gonna get C, right? Always gonna end up with that most C. Right? So you either get you either get Galileo's addition or you get C. So photon, let's say someone's traveling on photon. They shoot a gun. How fast is that bullet going? Good, that's it, right? That's the rules. Okay, so similarly, we then found that we had to transform coordinates, right? So we found out that time changes, and we took some pieces here and we created this thing called gamma. Right? Do you remember what gamma is? I just go actually to the coordinates here. So we have here X, and then my vector signs. So this would be for translation in the X direction, and no changes in Y. As I move the coordinate system, these are how all of these variables transform. This is the motivation, of course, for the upcoming 4 vectors. Because, and I'm just gonna like posit it really quickly. I'm gonna throw this nugget into your brain. Okay. Let's say you have a 4 vector. It has these components. I have showed you before how to take, say, the inner product of a blank. Right? What would that give you? The inner product of a blank. What is that called?
Isn't light already the zero coordinate?
So let's say you have the position vector. Okay, here's a point here and a point here, and they're connected by some vector v, or sorry, some vector r. Okay, and I ask you to take the inner product, which you interpret as the dot product. So what's the dot product of a position vector?
So like,
How long it is, right? The magnitude of that vector.
Yeah.
Good. Okay, so now I will ask you a more complicated question. Have a look at this 4 vector and tell me, do we take dot products the same way? Because you should know, right, with a 3 vector, of course, you would take the first component, you'd simply add it, right, to the second component and the third component. Right? Now we have a 4th component in time. So how is time treated? This is going to be the motivation for working with 4 vectors and with learning something called metrics. Okay. So in fact, you may notice that as you get to this part of your book, the structure of space-time itself, that while these are what we call Lorentz transformations. The appropriate way to do them is to treat time separately. And what I mean by that is that it takes a special place in our heart and our love. And we treat these as so x0, we're going to define as CT. And beta, we define as V over C. And x1 is just not from these, but just what does x1 mean when we think about it in the context of
when you move
tensors and everything else? Yeah, what does x1 mean?
further in time.
It's just x. And x2?
All right, oh, now I get it.
Like to say,
Okay. Okay. So I'm going to show you that I did a sneaky on you. What was the sneaky that I did that confused everyone?
Oh, you said X prime.
I didn't. Oh, I didn't? I didn't mean to. I said that I didn't mean it.
Oh,
So I have x0, I have x1, I have x2, and I have x3. Anything look suspicious?
oh, you put them to the powers instead of subscripts.
Ah, you put them to the powers instead of subscripts. So you might have looked at that and been like, what do you mean? X squared is not y. Okay. Unfortunately, we're going to get comfortable using this type of a notation as well. Because in general relativity and special relativity, we're going to use both up and down subscripts to denote different things. Okay, I know. So all of these indices and summation rules, they're annoying sometimes to think about, but they do make the writing a lot easier. Okay. So how would I write this tensor notation? So I want to rewrite this, and I want to write it in a better way. So let me first write the Lorentz transformations again with beta and whatnot. So I'm going to do x0 prime. And I'm going to use a bar here instead of prime because otherwise that would confuse. Okay. And x1, x2, x3. Okay, so what's this one? Excellent. What's this one? Good. This one? Not so easy to guess anymore, is it? Okay, so let's write it out. It's gamma. 1 minus beta x0. And this one? Yeah, unfortunately, kind of close. You remember what gamma is? If you're online and you don't know what gamma is, I can write it, but you know,
Right, yeah.
I can write gamma this for everyone else. You know what it is though, right?
Yeah, but-
Yeah. Okay, right. Very good. I know that, but you know,
Yeah,
can you explain it
but-
to the class? Yeah. Make sure it's written properly. Gamma here. So this was the same, that gamma was the same, gamma here. That will act to shorten or lengthen appropriately, depending on the relative velocity between the observer and the moving frame. Right? Okay, so let's continue writing really quickly. Well, here is simply that's not this. You know. How do I write that?
When you find her, right?
So if I wanted to write that in the matrix form, how do I write it? Is it possible?
Oh, yeah, it should be possible. It should be-
Yeah, but everyone's like, yo, fuck yeah.
Oh, yeah,
Obviously.
you can make that into a column. Column.
What's the left hand side look like? You want to actually write it out? We could write it out. All right, let's write it out. And then we'll shorten.
Oh, the left one will be x prime 0, x prime 1, etc.
Okay.
And then now we will, it can be two matrices, so I was thinking.
Can it be two matrices or is two matrices?
I think it is.
It's two?
I was gonna put like, I was gonna originally put, like, x1, x2, x0, x1, x2, x3, and then multiply by, what's it?
I think they one day since I do like a transformation matrix.
In fact, that's what it is, right?
Yeah,
You knew that
yeah, because it went.
because you remembered from your old learning. And also because we talked about this previously. What is it that we're doing? We're transforming, right? We're moving the coordinate system. So here's the new coordinate system. Well, that's simply the result. Something that looks like this times the original coordinate system, right? So what are the elements in here? There's definitely betas and gammas. Okay, let's do the easy ones. How does X3 transform?
Just one.
Good. Where?
In the 34th column.
Here? Read says in the bottom right. You like that?
Yeah.
Good. What else do we write?
Same thing for x2.
No, let's finish that row.
Oh,
Zeros. Good. Okay, so we have 1, 2, 3. Are we done? Let's go up, right? 1, 2, 3. Good. All right, now we'll cook it. Now we're cooking. Now what?
One, like, yeah.
Yeah. What else? Good. Okay, now we're cooking. Okay, let's do the easy ones. Okay, now we're out of easy ones. So now what do we do?
first column, first row should be just gamma.
First column, first row should be just gamma. Does that seem right?
Yeah.
Good.
And then first row, second column. Beta.
Beta over gamma.
Negative beta times gamma. Now they're flipped, good. So what is this one? Basic, right? Okay, so that was a hassle. I didn't like that at all. So let's write it like adults. How do I write this? Come on, we've been learning all about tensors and second orders and blah, blah, blah. How would you reduce this?
Oh, you wanted like subnotation?
What?
Do you want any subnotation?
Yes, please.
Okay.
Let's do the left-hand side.
X bar, put this X bar I.
Correct. That's how we write vectors, right?
What's the top?
Changed it.
You-
We can do it. We can do it on top. Let's do it right here. Equals.
Are we gonna use the dimensional thing?
We don't have to check.
Oh, X bar. X bar Y. We can use quantity of this.
No. What is this?
Equals zero.
Well, that's like,
What is this?
that's the transformation. We follow the transformation.
That's a transformation matrix, or how would you describe it in terms of tensors? A second rank tensor. How do I write that?
Oh, L.
Sure. Yeah, you can do L. I'm going to use lambda here.
There will be like I and J.
Exactly, an I and a J, right? Because we need to match the dummy indices. And then what else?
X to the power of 1.
Good. So is x to the power I here, or how are we going to do this? We need the dummy indices to.
I, J, and J.
Yeah. So in fact, here's the fun way to write it. We're going to keep the I in the ups so that we know that they're free. And we're going to give ourselves a little bit of a hint about which ones to sum by writing the J's that need to be summed in opposing, right, sub and superscripts. Does that make sense? And look at how pretty that is. That's gorgeous.
Secrets.
What?
Like, that's the version of secret.
Yeah, this is the secret version. Okay. Okay. So I want to take the dot product of 2 4 vectors.
Okay, so I need fourth grade.
So a 3 vector would be a 3-dimensional vector. A 4th vector is a 4th-dimensional vector.
So fourth grade.
No, remember what rank means. Rank, it does not tell us about the dimensionality. It doesn't tell me how many elements there are along the vector. It tells me how many individual orientations exist.
How many indices?
Yeah,
How many indices are
like
required?
dimensions.
Indices are not dimensions at all.
Because in here, it's only a second ring, because we only need I and J to communicate.
Yeah, it's 2D.
It's not 2D though. What does this describe? This describes 4 dimensions in space and time.
Yep.
Yeah.
And yet it's represented with 2 indices,
I and J.
right? So we have to kind of like break this in our mind that the dimensionality of a matrix doesn't necessarily represent the dimensionality of space.
Yeah, I thought like the dimension you could draw the matrix in.
Yes, yes, you can draw this in 2D, that's correct, with 2 indices. Right. but it describes four-dimensional space. Okay. So how do we take a dot product with four-dimensional space? You just do it? Okay, well, I'm gonna tell you how it's done. Time is separate and unusual. There's no space to put this. Or we're gonna put time. I already said, so here's what we're gonna do. I'm just gonna show you. We're gonna describe why this is in a little bit. If you have two vectors, A and B, A dot B in four space is given by minus A0, B0 plus A1, B1 plus 2, 2 plus B. Okay. So time is a little stupid. And for reasons that I don't have time to get into right now. When we're doing the inner product of a four-dimensional vector, we take away the contribution from the length. Okay. Okay. This thing here that we described before, it's with the Lorentz transformation matrix. You could similarly write this product as so like this. You knew. That's really stupid looking, but I promise it's helpful. Okay. This is called Minkowski metric or space-time flat space-time. Okay.
Then we'll learn what that does like next. Yeah.
Like that's as much information as I should give you, right?
Okay.
We're gonna dive into this more. It really will help for you to brush up. And in particular, just thumb through your notes. We're not gonna do the length contraction. We're not gonna do the variations of how things travel through space and time. We're going to talk about how this thing, the metric of flat spacetime, changes when spacetime is curved. And importantly, we are going to describe what it means to have a curved spacetime in the first place and what it is that curves space. Do you know what it is that curves space? Mass. Mass curves space. And therefore, you'll see it. And we will deal not only with the idea of a flat spacetime, we'll look at spherical spacetimes, we'll look at wormholes, we'll look at bubbles, so you can travel faster than the speed of light locally, right? So you'll get to learn about wormholes, you get to learn about warp drives, and we'll describe why they're all impossible. Because why you ruined my day. Okay, but that's the fun of general relativity. And along the way, if you want to, I would recommend this book, but you don't have to. We'll get enough of this stuff out of it. Along the way, we'll learn some really fundamental truths about the universe. So we're going to learn how GPS works. We're going to learn about what happens to stars after they die. And the most incredible thing is, of course, the prediction of black holes, right? Which Einstein was like, that's not possible. And everyone else is like, it's right there. And of course, he was wrong. Einstein is not wrong about a lot of things, but the things he's wrong about are legendary. Okay, any questions, comments, concerns? Okay, folks, I'm gonna let you go because I'm probably gonna vomit.
Real quick, house connection, can we find that in the, what book can we find the house metric? Just learning more about it.
It's in all of it, all three of the textbooks will reference it the same way.
Okay.
If you look up the Minkowski metric on Wikipedia, it's the most simple space-time, and it's this one here, which looks at a flat space, which says that X, Y, and Z are orthonormal, and T, which obviously you can't use your hand in that, is also orthogonal to it. But the way that it is related is by -1. Okay. No one in the chat.